Hello guys, so today I'll be explaining the physics AMS of term 1 week 10. So let's start. A substance is heated, meaning we're adding heat at a constant rate. The following diagram shows the variation of the temperature of the substance with time. Let me discuss with you about this diagram. First of all, we have 1, 2, 3 levels. If we have 3 levels, when you are considering a level, you're going to take the slope. So 1, this is 1, this is 2, and this is 3. That means we have 3 states. We only have 3 states when we're talking in physics. They are solid, liquid, and gas. So that means by seeing how many slopes we have, we deduce that we have solid, liquid, and gas. Next thing you guys need to know is that when it is a slope, okay, there is a change in temperature, but no change in state. So what's happening in the slope over here is that we started with a solid and we're slowly but surely adding heat to the solid. Then it will reach this point over here, this flat line. What happens in this flat line, which we call its melting point, okay? In this flat line there is no change in temperature, but there is a change in state. Meaning that once it reaches this point over here, which here we call the melting point, okay? Or if you remember from last week's quiz, we called it the ice point. All right? This point over here, which we call the ice point, there is no change in temperature, but there is a change in state. And the same thing applies for all of the sloped lines and all of the flat lines. This flat line over here, if you extend it, this point over here is the boiling point, or better known as the steam point. Now, another thing I want to discuss with you is the kinetic energy and the potential energy. What you need to know is that if it is sloping, there is an increase in kinetic energy, whereas potential energy stays the same. However, when it is flat, okay, there is an increase in potential energy, whereas the kinetic energy stays the same. So let me explain it in terms of particles. We start here, we have a solid. Solids have particles that are stuck together, okay, and they have a vibrating motion. They're stuck and they have a vibrating motion. As we add like heat slowly but surely, they start to move faster and faster until what? Until they reach their melting point, okay? Now, from A to B, when it is curving, we have only one state, which is the solid. However, when it is flat, from B to C, this is the melting point, so it's going to change from a solid to a liquid. Then again, from C to D, since we are sloping, we're going to have only one point, only one state, which is a liquid. And then finally, from D to E, and then from D to E, because we are a flat, and it is the steam point, which is the boiling point, it's going to change from a liquid to a gas. And now, finally, we have our final slope, which is the gaseous state on its own. So what we understand is that if it is sloped, there is a change in temperature, but no change in state. Also, if it is sloped, there is an increase in kinetic energy, whereas potential energy stays the same. And when it is sloped, you only find one state at a time. However, when it is a flat line, okay, you can find the ice point and the boiling point, which are the melting point and the steam point, okay? So ice point is melting point, boiling point is steam point. But when it is flat, there is no change in temperature, but there is a change in state. So let's explain it again by particles. A, we have a solid, it's like tough, stuck together. Then you're slowly adding heat to it until here. It reaches here, and what happens? It starts to melt. It stays at the same temperature, which is, I believe, 0 degrees Celsius for ice. So at 0 degrees Celsius, you've been adding heat slowly but surely to the ice cube, and then its particles started to move a little bit faster. So then in the solid and liquid state, when it is flat and the potential energy increases, whereas the kinetic energy is the same, so it's going to be changing from a solid to a liquid. Then after that, it will be fully transformed into a liquid. So then the liquid is what? Its particles move with respect to each other. So then we're going to add more heat until it reaches where it reaches its boiling point. Now, in its boiling point, it will stay 100 degrees Celsius for some time, okay? But then the kinetic energy stays the same, whereas the potential energy increases. And since we're giving it heat slowly but surely, it's gonna melt, and it's gonna not melt, it's gonna boil, and it's gonna change from a liquid to a gas. And then finally, you reach the gaseous state, which is the final state. So this is like around 6 minutes of the video. That was just an explanation of the graph. So they're telling us which parts of the graph correspond to the substance existing only in one state of matter. If you remember, it exists only in one state of matter when it is sloping. If it is flat, it exists in two states of matter. So, which ones are sloping? We have A and B that are sloping, we have C and D that are sloping, and we have E and F. So the answers are A and B, C and D, and E and F. Now, question number 2. We learned in physics some equations, okay? I'm gonna write them right now. So we have Q equals mct. Alright? I'll explain it right here and now, since it will come throughout the quiz, and I'll explain all of the equations that are related to this part of the quiz, okay? So Q is what? Is the energy required, okay? Or the quantity of heat. So the first equation, which is Q equals mct, we have Q is the energy required or the quantity of heat needed. Next thing, we have our mass, m. Then we have C, which is our specific heat. And then here I forgot something. It is delta T. So delta T is what? The change in temperature. Now the units. The unit of Q, which is the energy required or quantity of heat needed, is joules. The unit of M, which is the mass, is kg. Remember, in physics, whenever we're talking about mass, it is in kg. Now, the unit of the specific heat is in joules per kg times Kelvin. Not kilojoules. Pay attention to what they give you. You have to pay attention. Is it joules or is it kilojoules? And now finally, this is one of the most important ones. The unit is not specific, because delta T is what? Is temperature final minus temperature initial. So what's important is that always you take your answer in absolute value, of course. So what happens is that if you have the temperature in Kelvin, or if you have the temperature in degrees Celsius, if you subtract here and here, you're going to have it the same value. Yani, for example, let's take this. We have from 20 degrees to 80 degrees. So the change in temperature is 60 degrees Celsius. طيب, what if I did it in Kelvin? 80 plus 273 is 353. Minus 20 plus 273, which is 293. And then if we subtract them, 353 minus 293, you're going to get 60. So no matter the unit, if it's degrees Celsius or Kelvin, it's going to be the same. So what matters is that you do temperature final minus temperature initial. So anyways, let's start. A sample of 70 grams. We have mass, but in physics, whenever we have mass, we have to convert it to kilograms. So from grams to kilograms, we are going to divide by 1,000. And so we get 0.07 kilograms. Next thing we have is the specific heat capacity. Look at it, it's 385 joules. We need it in joules per kg times Kelvin. Here it is given to us in joules per kg times Kelvin, so this is correct. Okay, so now we have our specific heat capacity. Now, they told us is heated from 20 degrees Celsius, which is temperature initial, to 80 degrees Celsius, which is temperature final. So now what do we have? We have mass, we have specific capacity, and we have temperature final and temperature initial. So if we put them all together in an equation, we get Q equals M times C times temperature final minus temperature initial, which is delta T. Now, to make sure that our equation is correct, we're going to read what they want. They want the quantity of heat. Quantity of heat means Q. That means our equation is correct. So substituting, we get that Q is equal to the mass, which is 0.07 kg, times C, which is 385, times temperature final, which is 80, minus temperature initial, which is 20. If you do it on your calculator, you are gonna get 1617. And always the quantity Q is in joules. But pay attention, what do they need? They need it in kilojoules. So very simply, to change from joules into kilojoules, we are gonna divide our answer by 1,000. So now we get 1.617 kilojoules. So definitely, we're gonna round it. Let's say we're gonna round it to the first decimal place, or to one decimal place. So if you round it, it's gonna be approximately 1.6 kilojoules. So our answer is then 1.6 kilojoules. Question number 3. Below is the temperature time graph of a sample of matter being heated. Okay, they're telling us the phase change. Phase change means what? Phase change means the state change. Okay, and we said the only time the state changes, okay, is when we have a flat line. So looking back at our graph, we see we have a slope over here and a slope over here, and we have a flat line over here. So if we're gonna take the time interval in which the phase changed, we're gonna definitely take the flat line. So pay attention, the flat line starts at 2 minutes and ends at 8 minutes. So it's from 2 minutes to 8 minutes. Here I think they put the unit wrong. It's not seconds here, it's given in minutes. So anyways, it is from 2 minutes, okay, until 8 minutes. Now we move on to question number 4. Okay, this is very important. Remember, we said we have the first equation, which is Q equals mc delta T. Now, I'm gonna add one new equation, which is Q is equal to mass times LE, which is the specific latent heat of vaporization. So now, our new equation is Q, which is the heat or energy required, is equal to M, which is the mass, times the specific latent heat of vaporization. So here I'm going to call it specific latent heat. By the way, what does latent heat mean? Latent heat means hidden heat, okay, of vaporization. Now, after solving this question, I will explain to you when we use this and when we use this, and then you will see the relation between the both of them. So we have the boiling point of mercury is 357 degrees Celsius, and its latent heat of vaporization, which is LE, is 300 kilojoules per kg. Anytime we're talking about specific heat, specific latent heat of fusion, or specific latent heat of vaporization, our unit should be in joules per. Either, if we're talking about specific heat, it should be joules per kg times Kelvin, or if we're talking about specific heat of vaporization or specific heat of fusion, then it's going to be joules per kilogram. So basically what I'm saying is that you should change this into joules. To change it into joules, we're going to multiply it by 1,000, so it becomes 300,000 joules per kg. So this is the specific latent heat of vaporization. Now they need what? They need the energy needed, so Q, to completely change a 0.150 kg sample This is what? This is the mass, and it is in kg, so we keep it as it is, of mercury from liquid to gas at what? At the same temperature, which is the boiling point. So if you're gonna do temperature final minus temperature initial, you're gonna get 0. But if we multiply it by 0, what's gonna happen is that we're gonna get 0 as the quantity required, but in reality we need a quantity. So in this equation, we're not gonna use the temperature. Instead, we're gonna use the equation that Q is equal to the mass times the latent heat of vaporization. So we have the mass, which is 0.150 times the latent heat of vaporization, which is 300,000 joules per kg. So then it becomes 0.150 times 300,000. And so then we get 45,000. But pay attention here. Remember that Q is always in joules. So here we have what? We have our Q in joules, but they need it in what? They need it in kilojoules. So very simply, to change from joules to kilojoules, we are going to divide by 1,000. So 45,000 divided by 1,000, we get 45. So the energy needed to completely change a 0.150 kilogram sample of mercury from liquid into gas at 357 degrees Celsius is 45 kilojoules. So going back to the graph, it would look something like this. We have liquid, liquid gas, gas. What I'm going to tell you, please pay attention. When we are sloping, okay, that means we have a change in temperature. We use the equation Q equals M times C times delta T. Here, since we're talking about gas, we're going to use the heat of vaporization. So when we are flat, when the line is flat and we don't have a change in temperature, then we use the equation Q is equal to the mass times the latent heat of vaporization. And then as you slope again as a gas, to find the energy needed, it's going to be Q equals the mass times the C times delta T. However, if we are, of course, like talking about a solid to a liquid change, so solid, solid, liquid, liquid, okay, here we would also use Q equals MC delta T. However, here we would be using mass, so Q is equal to the mass times the latent heat of fusion. And then here again, we're going to be using Q equals M times C times delta T. So what's very important is here, it reached the boiling point. So it gives us a hint what we're going to use. We don't have a change in temperature. Because if you do temperature final minus temperature initial, you're going to have 0. And as we do not need 0, we cannot use 0 as our change in temperature. So instead, we're going to use that Q is equal to the mass times the latent heat of vaporization. Now we move on to question number 5. The energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius is called the specific heat. So, if you remember in chemistry, we used to denote C as what? It changes 1 gram by 1 degrees Celsius, okay? To raise the temperature by 1 gram of 1 degree Celsius. But now, since we're talking in physics, and we know that the mass in physics is in kilograms, it changes. So C is the energy needed to raise 1 kilogram. So 1 kilogram of a substance by 1 degrees Celsius. So anytime you see energy required to raise temperature of 1 kilogram by 1 degree Celsius, immediately you put specific heat capacity. Now we move on to question number 6. Okay, this is very important. In this chapter, we discussed only 3 specific heat. We have the basic specific heat, okay, which is denoted by C, okay. Then we have the specific heat of vaporization. Vaporization means changing from a liquid to a gas. It's denoted by LE. And then we have the specific heat of fusion. And fusion is what? Changing from a solid to a liquid, and it's denoted by LF, okay? So, in this chapter, we only learned 3 specific heats, which are the specific heat of the basic one, which is denoted by C, then the specific heat of fusion, which is denoted by LF, and the specific heat of vaporization, which is denoted by LE. So if we're going from a solid to a liquid, and we're what? We're required to turn 1 kilogram, okay? The keyword is 1 kilogram, okay? Then it is what? The specific latent heat of what? We're going from a solid to a liquid, so it is the specific latent heat of fusion. However, we're going in the next one, 1 kilogram of a substance from a liquid to a gas, okay? So then we call this what? We call it the specific latent heat of vaporization. Now we move on to question number 7. And here we're gonna learn a new rule. And this new rule is Q is equal to I times V times T. Q, as we know, it is the heat or energy required, okay? And it is denoted in joules, J. I is the current and it is denoted by A. V is the voltage and is denoted by V. And finally, T is the time and it's always denoted by seconds. The time is always in seconds, okay? So the new equation that we learned is Q is equal to I times V times T. Now, in this question, we are going to learn a relation between this and this. Okay, let's start. In an experiment aimed to measure the specific heat of aluminium, an immersion heater is inserted inside a 1 kg. This is our mass. We have our mass, which is 1 kg. Aluminium block as shown below. Now, if you go down, okay, we already have our mass, which is 1 kg. Then we have our time in seconds, which is 110 seconds. Okay, then we have our current in amperes, which is 2 amperes. This is our current, I. Then we have our change in temperature. Our change in temperature is 3. And now we also have what? We also have the voltage, which is 12 volts. Okay, and again, they gave us the time. So what they're asking us to find is the specific heat capacity of aluminium. Now my question is, we have mass, we have time, we have current, we have change in temperature, and we have voltage, and we need to find the specific heat capacity. Let's write all our given. We have mass, we need to find the specific heat capacity, okay? We have delta T, we have then current, we have voltage, and we have the time. So what we can do is we can make a relation. We know the equation is Q equals mc delta T, but we also know the equation Q equals I V T. So if this Q is also equal to the same exact Q, because they're both Q, they're both the same, then we can write that I V T is equal to m times c times delta T. And then by substituting, we will get the answer. So our I is 2, becomes 2 times the voltage V, which is 12, times the time in seconds, which is 110, is equal to the mass that we found, which is 1 kg, times C that we need to find, times the change in temperature, which is 3. So now, making an equation, we're going to get that C is equal to 2 times 12 times 110, okay, divided by 1 times 3. So if you do it on your calculator, 2 times 12 times 110 divided by 1 times 3, you are going to get 880. But we have it as C. And what is the basic unit of C? The basic unit of C is joules per kg times Kelvin. They need it in joules per kg times Kelvin, so we are safe. So our answer is 880. So we come here and we put 880 as our answer. Question number 8. Remember, during a change of state, whenever we're changing the state, okay? This is our graph. Here, for example, it's solid. Here, it's solid liquid, so we're changing the state, and here it is liquid. Whenever we're changing the state, there is no change in the temperature of the body. So during a change of state, added thermal energy will not change the temperature of the body. Instead of changing the temperature of the body, it's being absorbed by the body as potential energy. So that's why when it is flat, the potential energy increases. Now, the specific latent heat of fusion, LF, is the heat energy needed to change the state of 1 kg. Remember, LF changes 1 kg of matter from the solid state to the liquid state without any change in temperature. Okay, so here it is 1 kg and here it is temperature. So that's question number 9 done. Now we move on to question number 10. They told us the graph below shows the temperature of a liquid at the vicinity of its boiling point. They're telling us the heat energy supplied to the liquid at its melting point. So here, during its change in state between points 1 and 2, so they're talking about this flat line over here. They're telling us the heat energy supplied, okay, what form of energy will it increase? Or they're saying the heat energy supplied will be used to increase what form of energy of the molecules. Remember, we said on the flat line, okay, there is an increase of potential energy. However, on a sloped line, there is an increase of kinetic energy. So here, the answer is potential energy. Now this is something from last week's quiz, but I will rewrite the equations again. We have that the change in energy is equal to a constant times the temperature. However, we have that the speed is equal to the radical of the temperature. So now that we know these rules, we can reapply them here. They said a fixed amount of gas is kept at a temperature T. The average speed S of its particles is V. So now they denoted S as V. And their average kinetic energy, they denoted it as E. Okay? The temperature of the gas is then quadrupled. So now what happens? You're multiplying the T by 4. And here you're also multiplying the T by 4. So what happens is that if you multiply over here by 4, then you also have to multiply here by 4. However, if you multiply here by 4, they are all under the radical. So what happens is that you'll have to multiply S by radical of 4. So radical for S is equal to radical temperature times 4. So then solving it, you will get 2 times the average speed is equal to 2, because the radical of 4 is 2, times the radical of the temperature. So if we quadruple the temperature, the average kinetic energy also quadruples. However, the average speed, as we did, it is multiplied by 2. So over here it is 4e now, and over here it is 2v. Now question number 12. Here we're going to apply one of the past equations we learned, which is Q equals mc delta T, and Q is equal to I times V times the time. So let's read the specific heat capacity of copper. So we have C of copper, and it is already in joules per kg times Kelvin, so we keep it as it is. Then the temperature of 1 kg, which is the mass sample of copper, is being raised by a heater marked 2 amperes, 12 volts. So we have the current I, and we have the voltage V. Then they gave us the time in seconds. Okay, the temperature of the sample will be raised to the nearest integer. So now they want us to find what? They want us to find delta T. So notice, we are given the mass, we are given the C, we are given the I, we are given the V over here, and we are given the T, but we need to find the delta T. So the equation we're going to put is that since Q is equal to Q, mc delta T is equal to I V time. So the mass, which is 1 kg, times the C, which is 380 joules per kg times Kelvin, times the change in temperature that we need to find, is equal to I, the current, which is 2, times V, the voltage, which is 12, times the time, which is 300 seconds. So then, if we put delta T over here, we're going to have delta T is equal to 2 times 12 times 300 divided by 1 times 380. If you do it on your calculator, you are gonna get it to be 18.9, but they need it to the nearest integer, so you're gonna round it, and it is gonna be 19 Kelvin. So our answer here is 19 Kelvin. Now we move on to question number 13. Here I'm gonna write a new equation which is very similar to the specific heat of specific latent heat of vaporization, but it's only for fusion. So Q is equal to M times LF. Okay, this is where Q, the energy needed, is equal to the mass in kg times the heat of fusion. So let us start reading. We start reading by that we have a mass, but our mass is in grams. So to change it from grams to kilograms, we are going to divide by 1,000, and over here we get 0.05. Then after that, this is the mass of what? This is the mass of the ice cubes. Then we have the mass of water, which is 0.8 kg. Okay? At a temperature which is 27 degrees. So this is temperature initial, let's say. Now we have what? We have the specific heat capacity of water. So this is C, which is 4.2 times 10 to the power of 3. And the latent heat of fusion of ice. So this is what? LF. But make sure that it's always in joules. So here it is in joules, so we are safe. Okay, we can proceed. So we have mass of ice, mass of water, temperature initial, we have C, and we have LF. So they first ask us for the energy, which is Q, necessary to melt. So melt means we're going to be using the latent heat of fusion, the ice cube. So we're going to be using the mass of the ice cubes to the nearest integer. Very easily, we know the equation is equal to Q equals M times LF. Our mass is 0.05 kg times LF, which is 3.4 times 10 to the 5. And then if you do it on your calculator, you are gonna get 17,000, my bad, 17,000 joules, but they need it in kilojoules. So very simply change it from joules to kilojoules by dividing by 1,000, and then you will get 17 kilojoules. So you have the answer for the first one, which is 17 kilojoules. Now, this is very important. They need the temperature of the resulting liquid. We have Q over here, which is 17 kilojoules. Now they need the temperature, which is temperature final. Knowing we have temperature initial, we have C, and we have mass of the liquid water, which is 0.8 kg. We can solve the equation very simply by applying the rule Q equals MC delta T. Okay? So Q given from here is 17 kilojoules, which is 17,000 joules. Okay? It's equal to the mass of liquid, which is 0.8 kg, times the C, which is 4.2 times 10 to the power of 3, okay, times the change in temperature. We have temperature final that we need to find, but we are given temperature initial, which is 27 degrees. Of course, put it in the absolute value. So, to find temperature final, very simply, we're going to move this first to the other side. So we get what? We get 17,000, my bad, 17,000 divided by 0.8 times 4.2 times 10 to the power of 3. If you do it on your calculator, you are going to get 5.05. So they told us 5.05 is equal to temperature final minus 27. But of course, it is an absolute value. So if you remember from math, whenever we have an absolute value, we can switch the signs. So that means what? It is now 5.05 is equal to the absolute value of 27 minus temperature final. So from now on, to not confuse, what you're going to do is you're going to take the big temperature, or the temperature of, for example, let me explain to you like this. If you have a solid and liquid, always take temperature final as the temperature of the liquid. If you have liquid and gas, always take temperature final as the temperature of the gas, or the state that is more free, okay? So in this case, what is more free, the ice cubes or the liquid water? Definitely the liquid water. Okay, so now we're going to close the absolute value, and we move 27 to the other side. So we have that temperature final is equal to 27 minus 5.05. If you do it on your calculator, you are going to get 21.95. So if you round it, it's approximately 22. Here we don't have 22 as an answer, so we're gonna take 21, okay, as our answer because it's nearest to the 21.95. And then here our answer was 17. So let me explain one more thing that I forgot to mention, was that you're adding ice cubes to liquid water, okay? So that means the temperature of the liquid water is gonna decrease, whereas the temperature of the ice cubes is gonna increase. Here, they're asking us for the temperature of the resulting liquid, so they're mentioning liquid, and we said since it's going from the solid to the liquid, okay, or like we have a solid and a liquid, then definitely if you add the ice into the water, then you know that the water is gonna cool down, the temperature is gonna decrease, whereas the ice cubes are gonna heat up, or their temperature is gonna increase. So that's question number 13 done. Now we proceed to question number 14. Here we first have mass. This is our mass in kg. Then we have our voltage and we have our I, which is the ampere or the current. Then they gave us a graph of the sample's temperature versus time. We go down. They told us that the time that elapses before the sample begins to melt. So you look at the graph, let's zoom in, and you go to the time exactly before it starts to melt, exactly before it starts to become flat. So here it is approximately 120, 110, 20, 30, so 140 seconds. So here the time elapsed before it melts is 140 seconds. Now we need to find the specific heat capacity of ice. To find the specific heat of capacity of ice, so now we're going to take 0.20 kg as our mass. This is our voltage, and this is our current. And I remember that the time was 140 seconds. They need us to find C, but we're only missing what? The delta T. So very simply, to find the delta T, you take the last point, you take the first point. Okay, so here the first point is minus 10. Okay, let's say this is temperature initial. We're going to subtract it from the temperature final, which is 0, and we're going to put it in absolute value. So we are going to get minus 10 in absolute value, which is 10. So now we have delta T, which is 10. So now if you remember, we have Q is equal to MC delta T, and we have Q is equal to IV times the time. Okay, we have the mass, which is 0.2. We have C that we need to find, and we have delta T, which is 10. And then here, we have I, which is 2.5. We have V, which is 12, and we have the time, which is 140 seconds. So very simply, since Q is equal to Q, we can make them equal to each other. So 0.2 times C times 10 is equal to 2.5 times 12 times 140. So then you get that C is equal to 2.5 times 12 times 140 divided by 0.2 times 10. Do it on your calculator. You are gonna get what? That C, let's bring it over here. We're gonna get that C is 2,100 joules per kilogram times Kelvin. But if you go down, they need it in 10 to the power of 3. We have 2,100 joules per kg times Kelvin. So how do we change it from this to 10 to the power of 3? Very simply, just do your answer, which is 2,100 divided by 10 to the power of 3, and you are going to get 2.1. So the answer over here is 2.1 times 10 to the power of 3 kilojoules. My bad, not kilojoules. Joules per kilogram times Kelvin. Then we reach question number 15. We have a 200 gram. 200 gram is mass, so we change it to kilogram. By dividing by 1,000, we're going to get 0.2 kg. Okay, so remember the mass is 0.2 kg. They told us drag and drop the correct answers to compare the energies based on the above graph. Okay, so this is something really technical. I'm going to put them in order, and then I will explain each one why. So here we have the energy to melt 200 grams of ice. If it is melting or boiling, okay, or they tell you LF or LE, that means the latent heat of fusion or the latent heat of vaporization. If they tell you any of these four, then it has the maximum energy, okay? It has way more energy than to simply heat something. Now, of course, okay, water has more energy than ice, because water is a liquid, whereas ice is a solid, okay? That means ice, its particles are moving really, really, really slowly, okay? So that's why when we're heating ice, okay, then we call this what? We say this has minimum energy. When we're heating water, we say this has like in between energy. And whenever we're melting, boiling, okay, or they're telling us about fusion or vaporization, then it has the maximal energy. So now here we're gonna learn a new equation, which is not new, but it's like power is equal to the quantity of heat or energy needed over time. So let us first find our quantity of heat, divide it by the time, and then we'll be able to find the power. If we go up, we are given that our mass is 0.2 grams. But then we need to find the heat and we need to find the time, since we are already given that the specific heat capacity is 2.1 times 10 to the 3 joules per kg. So by looking at the graph, we see that the change in temperature is minus 10 in absolute value, minus 0, which is 10. So the delta T is 10. We know Q equals mc delta T. Delta T is 10. C was 2.1 times 10 to the 3, and then m was 0.2. So by doing it on our calculator, we are gonna get 4,200. But this is not what we're looking for. We're looking for the power. And we know that power is equal to Q over the time. So let's find the time, okay? Remember 4,200? Here it is 50 seconds. So the power is equal to Q over T. Our Q was 4,200. Then divided by the time, which is 50 seconds. And then we're gonna get 84. So our answer over here is 84 watts. Question number 16. So now again, we have a temperature versus time graph. We have what we have, the mass, which is 0.1 kg, and we have the power, which is 50 watts. We go down, they're asking us for the boiling point of ethyl alcohol. So we go up, we're gonna see at which temperature does ethyl alcohol boil. So here it boils always on the flat line, so it is almost 75 degrees Celsius. Now they need us to find the specific heat capacity of ethyl alcohol up to two significant figures. We have power, which is 50 watts. We have the mass, okay? We can find the delta T and we can find the time. So very simply, we know that Q is equal to, Q over T is equal to power, and Q is equal to M times C times delta. Okay, so very simply, let me write the equations again. Power is equal to Q over T, and Q equals MC delta T. We have the mass, which is 0.1. We need C to find it. We can easily find delta T by doing what? By taking this point over here, which is 75, and subtracting it from this point over here, which is 10. So 75 minus 10 will be 65, which is the delta T. Now we have the power, which I believe was 50 watts, is equal to the Q, which we need to find over the time. By checking the time, it is almost 340, I would say. So 340. So 50, the power, is equal to Q over 340. Bring 340 to the side, you're gonna get that 50 times 340 is equal to Q. If you do it on your calculator, you are gonna get 17,000 joules. Now, we know Q equals MC delta T, okay? Our Q is 17,000 joules, is equal to the mass, which is 0.1, times C, which we need to find, times delta T, which is 65. So then we make an equation. We get C is equal to 17,000 divided by 0.1 times 65. So it becomes, if you do it on your calculator, you are gonna get 2615.38. Okay, they needed the two significant figures in scientific notation. Okay, so if you round it approximately into scientific notation, it's gonna be 2.6 times 10 to the power of 3. So our answer over here is 2.6 times 10 to the power of 3. Question number 17. Now, after the temperature in a room drops from 25 degrees Celsius to 20 degrees Celsius, so temperature initial, temperature final, 50 grams of water vapor, this is what the mass, but we have to change it, sorry, into kilograms, so we divide it by 1,000, and it becomes 0.05 kg. Then we are given what? We are given the specific heat of vaporization, which is LE, and the specific heat capacity, which is C, is 4.2 kilojoules per kg 2 degrees Celsius. So here, this is where we need to pay attention. Here they told us kilojoules, not joules, so we need to change it into joules. It becomes 4.2 times 1,000, which is 10 to the power of 3. So times 10 to the power of 3 joules per kg times degrees Celsius. So now I'm going to explain it in another way. Or not in another way, in a deeper way, okay? They told us after the temperature in a room drops, okay? So we start with temperature initial to temperature final. Then we have the mass, which we found in kilograms to be 0.05 kilograms. So this is first what? Temperature initial, temperature final, then the mass, which is 0.05 kg. Then we also find that we are given C, which is what? 4.2 kilojoules. So then we converted it to joules. So 4.2 times 10 to the power of 3 joules per kg times degree Celsius. So what I'm going to explain here is very complicated. So please, please, please pay attention. Okay? We have two different things happening. First of all, we have a condensation. Okay? Condensation or evaporation can be using the same equation. يعني if we used for evaporation Q equals M times L E, then we can also use for condensation Q equals M times L E. So that means we now know the equation for condensation. But the second thing is what? Is that the temperature in the room drops. So that means what happens? It's cooling down. So we not only need to find the heat released means given off from the condensation, but we also need to find the heat released from the cooling. So very simply, what you need to do is take the total amount of heat is equal to the cooling heat plus the condensation heat. Okay? So very simply, to find the cooling heat, we have the mass. We have Q is equal to the mass times the C times the delta T. Because in cooling, there's a change of temperature. But then there is a condensation as well. But when we're condensing something, there's no change in temperature. So we're going to use the equation Q is equal to M times the latent heat of vaporization. So very simply, I'm going to clear it out. Then I'm going to solve. Again, we have Q equals MC delta T and Q equals MLE. We have the change in temperature, which is temperature initial, temperature final. So temperature final minus temperature initial in absolute value, we're going to get 5. So delta T is 5. Then we have the mass, which was 0.05 kg. Then we have C, which is 4.2 times 10 to the 3 joules per kg times degrees Celsius. So now we get Q is equal to the mass, which is 0.05 kg, times the C, which is 4.2 times 10 to the 3, times what? Times the delta T, which is 5. So we get the first energy, which is 0.05 times 4.2 times 10 to the 3 times 5. And it is going to be 1050. Now, for the condensation, we're going to do Q is equal to M times the latent heat of vaporization. The latent heat or specific heat of vaporization of water is in kilojoules. So we need to change it from kilojoules, okay, into joules. So it becomes joules per kg. Okay, simply by multiplying it by 10 to the power of 3, it becomes joules per kg. Again, we have the heat in kilojoules. So to change it to joules, we're going to multiply it by 10 to the power of 3. So very simply, to find the Q of condensation, it's going to be the mass, which is 0.05 times LE, which is 2,400 times 10 to the power of 3. If you do it, 0.05 times 2,400 times 10 to the power of 3, you are going to get 120,000. Okay? So this is actually the way how to do it. So when you're going to do it, you're going to have 120,000 plus 1050 is going to be 121500. Okay, then you're going to change it from joules into kilojoules. So again, it's going to be 1210. Okay, so now you have 120,000 plus 1050, and then it's gonna be 121,050 joules, and then you have to change it into kilojoules. It's gonna be 121.05 kilojoules. Now this is the correct way to do it. I believe in the SDP they are very wrong, because what they mean by the amount of heat released means the amount of heat that is released from the cooling when the temperature drops and from the condensation. Okay, I also checked my sources online, and yes, my way is the correct way to do it. But in the SDP, they're wrong. I believe what they did in the SDP was that Q equals M times LE only. So they only did this and they got 120,000, and then they converted it into kilojoules and they got 120 kilojoules. So it's wrong, okay? I'm going to put 120 kilojoules, but it's wrong. The correct answer is actually 121.05 kilojoules. I checked my answers online. If you guys want to double check, you can. But I'm pretty sure that this question is wrong. The answer is wrong because this is supposed to be its answer. Anyways, question number 18. They told us drag and drop the correct answers to complete the diagram describing the heating of methanol. So of course, what they mean by heating is definitely we're going to start with a solid. Why? Because it is below 0, because here on this point over here the temperature is 0. So since we start below 0, then it is definitely a solid. So we're gonna first start by heating a solid up. After that, it reaches the melting point. So over here we call this a melting point. Then again, it's sloping, but we are now heating a liquid, and then after heating a liquid we have the boiling point. So again, we start with heating a solid. Then when it becomes flat, it's melting. Then when it slopes, again, it's heating a liquid. Then when it is flat, it is boiling. Now finally, we reach this, which is very simple. They told us the center of mass of different irregular shapes is shown below. Select the unstable shape. Unstable shape meaning if you draw from its center of rotation an arrow and it does not pass through the base, then it's unstable. This is definitely unstable. This passes through the base, it's stable. This passes through the base, it's stable, and this passes through the base, it is stable. So this one is unstable. So let's submit and see. Inshallah, we don't have any wrong, except for question number 17, which I told you is wrong. Okay, alhamdulillah, alhamdulillah, we don't have any wrong. But question 17 here, look. As I said, they did this, which is wrong. Okay, according to my solving and according to what I found on the internet, the other way was correct. So this over here is wrong. So just quickly, I'll write the equations. We have that energy is equal to constant times the temperature. Then we have that the speed is equal to the radical of the temperature. Then we have Q is equal to MC delta T. Then we have Q is equal to IVT. Then we have that Q is equal to the power times the time. Then we have Q is equal to the mass times the latent heat of vaporization, and then finally Q is equal to the mass times the latent heat of fusion. So these are 1, 2, 3, 4, 5, 6, 7 equations we need for this exam. Thank you guys for watching, and I hope you enjoyed.